our Blackboard system for submitting our work. And Blackboard has a very strict deadline. And when you are late with your submissions, Blackboard is brutal. It just cuts you off and it will not let you submit. Don't really want to have to deal with late midterms, so please be mindful of the fact that this midterm is due when it's due, and that's it. And just to be clear, I'm going to bring out the calendar. So you can see here the midterm is due on the 29th, and that is at midnight. And if you're waiting till the last minute to submit a midterm that you basically have 2 weeks to do, it's a big mistake. That's a lousy strategy, because things will happen. Computers will die, internet connections will get lost, someone will have a snowstorm and they'll lose power. I don't know what's going to happen, but something will happen. And just waiting till the last minute, it's a really, really bad strategy. This is due when it's due. I know some people say, oh, I've had a difficult week and blah, 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 and I forgot and I overslept and I don't know what else. But, this is, your grade. Kind of important. It's like a third of your grade. So try to see if you can't submit that on time. And in the last class, we were preparing for Homework 7 to be submitted in the evening. Did anyone have any leftover questions from Homework 7? All right, Homework 7's done, so. How about questions that you might have had on the midterm? I know some people have tried it, because I saw some attempts. Any questions about the midterm that might be lingering that you'd like me to cover? No questions? Sure. 24 is a 3 to 8 line decoder. Let's see. So there's 24. That's a picture. And this is a 3 to 8 line decoder. And you can see it's an 8 line output. And you can see there's the 3 selectors being used. So that's 2 to the 3 outputs, right? So if you see 2 to the 3 equals 8, that's why you got 8 outputs there. And so then they're all inverted. They're all inverted. And then if you want to throw on the NAND gate into lines 3, 5, and 6, then you're going to get row 3, row 5, and row 6 to be asserted as a 1. Any questions about that? So it says here, f is equal to 1 when... And you tell me. Ashley, when is f equal to 1? Are you with me, Ashley? How about Brendan? Brendan, are you there? Oh, Ashley, no, it's all right. It's all right. Did you understand about how the truth table was obtained? Okay. And can you tell me what do you think maybe the answer might be for question number 24? Well, let's use a process of elimination. Will f be equal to 1 when all three inputs are logical 0? So here all three inputs are logical 0 and f is not equal to 1, so that's false. Will f be equal... Right. That's correct. So the choices are either all three inputs are 0 or 2 out of 3 inputs are 0. So if you look in here, there's 2 out of 3 inputs, they're 0, but it's still not 0. So that's eliminated. Okay, so that's not one of the choices, though. The other choice is 1 out of 3 inputs are logical 0. So then that's what it is, and that's it. So that's how you do 24. Yeah. You got to look at the choices and figure out which one fits the description of the truth table. Any other questions about this 24? Everybody understand that? 24. How about another question for me about this midterm? Let's do 23. And 23 is just like 24, only with a difference. And the difference is it's not a decoder, right? Because this was a decoder. This is an encoder, or what's known as a multiplexer. Encoder. Multiplexer and encoder are the same. So here's F now, and he's got inputs 0, 1, 0, 1, 0, 1, 0, 1. And then and now we look at the truth table that comes from this. And let's see. Tyler, what do you think you could use to describe F? Simple equation for F. Just now? Oh, that's all right. It's question 23. We can save you for a different question. Let's see. How about Brendan? Brendan, what do you think? I said, Brendan, what do you think? Yeah. What would F be equal to? That's correct. That is exactly right. So F equals Z, and that is one of the correct choices that's available to you. Right, you wouldn't say F equals Y, because that's not true. You couldn't say F equals Z prime, because that's exactly wrong. And F doesn't equal X, because it doesn't even look like X. And it doesn't equal X or Y prime, so the only thing left is X equals Z, and you can see it equals Z. You can just model it with a wire. In fact, you can wire Z to F, and that's the easiest possible implementation, really. Other questions about this question, question 23? Everybody sort of understand how these things work, these multiplexer thingies? How about another question for me on this midterm? Oh, alrighty. Let me go back to homework 7. Well, now, which question are we talking? Let's do question 19. Convert the following decimal number to binary using 6-bit 2's complement representation. So it's question 19. This is homework 7. And we have 13 base 10 equals what number in base 2? Using 6-bit 2's complement representation. So this is 13, 1, 1, 0, 1. 6 bits means 1, 2, 3, 4, 5, 6. And that is a correct answer. So it didn't say find the negative 13. It just said using 6-bit 2's complement representation. So I needed 1, 2, 3, 4, 5, 6, that 6th bit to be the sign bit. But it's positive. It's a positive sign. Did that sort of throw you? Because deleting zeros. If you did the 2's complement, then you'd have 1, 1, 0, 0, 1, 0 plus 1, and you would have 1, 1, 0, 0, 1, 1, and that would be equal to minus 13 base 10. Now, if you wanted minus 13 base 10, then that would be an answer. But because we're looking for the 2's complement representation with 6-bit format on 13, not minus 13, we do not do the complement and the increment. Okay? Sure. Any other questions about homework 7? Now that I've got it open. All right, so then what I'll do is I'm going to go back to the midterm. Just bear with me just a minute. I'll get to the... All right, the midterm is now opened. What questions do you have for me about the midterm? I'm just scrolling through. Sorry, what did you just say? 23. 23. Okay. So this is a didn't we just do 23? Yeah, we just did 23. Yeah, here, see? That's 23. F equals E. And any other questions that we haven't already done just now? You guys going to keep it. And could you do 24 too? Yeah, we did that. Other questions? No other questions? Really? Okay. Number 67. So, if you want to do a 2 by 2 binary multiplier, This is number 67. I made a mistake. Dear me. So this is the row numbers, but the thing you're actually multiplying is A times B. So that's 0 times 0, 0 times 1, 0 times 2, 0 times 3, 1 times 0, 1 times 1, 1 times 2, 1 times 3, 2 times 0, 2 times 1, 2 times 2, 2 times 3, 3 times 0, 3 times 1, 3 times 2, 3 times 3. Right, so that's 0 times 0. You can sort of see that's 3 times 1. So now, I'm just going to write out the answer in decimal. So that's 0, 1, 0, that's 0, that's 0, that's 0, that's 1, 2, 3, 0, 2, 4, 6, 0, 3, 6, 9. Now that I've written it out in decimal, I'm going to encode the output in binary. So now, what do we see for C3? C3 equals A1, A0, B1, B0. All right. So if we look at the actual output for C3 in terms of the circuit diagram, and it's a little bit difficult to draw. The thing to do is to take the drawing and annotate the intermediate results, which would require me to redraw the entire thing and reproduce it here. I don't know if I have a copy of it here. I don't think I do. That would be the thing to do, would be to make a printout, but I don't want to take time. But once you do, work through the expression as the schematic has been presented, you will see that is the case for C3. And similarly, you could look at C0, and if you like, you could get an equation for C0, and it would be something on the order of A0 and B0, I think. Let's see. A0 ANDed with B0. Yeah, that's a 1. That's a 1. That's a 1. And that's a 1. So C0 be A0 ANDed with B0. And then if you wanted to do a similar thing for C, it's not good to do this by inspection. What you really want to do is you want to take a printout of the actual circuit diagram and write the intermediate results from each one of the gates and get your simplification. Or, if you prefer, you can use your K-map. This would be a 4-variable K-map, and you could do it like this: A, B, C, D, if you like. And then I relabeled things just so that you'd be used to it. But in the case of our application, this would be B1, B0. And you can number. And then if you wanted C1, be 6, 7, 9, 11, 13, 14. Right, 9, 11. Yeah. And all the rest would be 0. Well, let's call on people. Brianna, what should I loop? It looks good to me. And what would be the product terms for that, do you think? Yep. So then you would look for this expression for C1 and see if you could get that from the from a simplified version of the schematic diagram. So basically you would have to redraw it and then annotate it, or print it and then annotate it, and that would give you an expression that's equivalent here. It would take a little time, but eventually you would find out that yes, indeed, what you have there is a 4 by a 2 by 2 binary multiplier. And so that's the upshot of all of this. Now the way you could do it, another way you could do it, is if you could write it this way. So then what you'd have is B0, A0, A1, B0, and then you'd come down over here and you'd write A0, B1, and then A1, B1. Now, if you wrote it out that way, symbolically, then you could just do simple addition. C1 would be A0, B0. And then you'd have these two numbers added, and you'd have to do the carry look ahead. You'd have to take the carry out when you added these two. So you'd do this with an exclusive OR, which is what we're trying to show in the diagram. So there's a couple ways to do it. You could try and write out the multiplication in this way. But maybe the easiest thing to do is just to do it as I've done, writing out the truth table, getting your minimum sum of products form, and then seeing if you can match that form, or match the canonical form if you like, with the gates that you see in the schematic. Actually, matching the canonical form with the gates that you see in the schematic is basically the same thing as trying to match the truth table. So that's actually a good way to go. You don't even need a minimal form here. If you can match the truth table with what is being produced in the schematic, then you know that you have met the specification for a 2 by 2 binary multiplier. And in fact, being able to do this exercise right in through here is a great way to find different ways to do implementations. And now that I think about it, you could probably do it with a decoder and a few OR gates, and that would be a way to do a multiplier very efficiently. But that's another approach to design. There's always more than one way to design something. So answer for 67 is true, and I hope this wasn't too complicated for you, but there it is. Any questions about 67? Any other questions about the midterm? Grabbing a fresh sheet of paper. '69. What is the 2's complement binary representation of decimal number 13? Oddly enough, I think we just did that. It was... Didn't we just do that? Let's see. Oh, because it's not 6-bit. That's the deal. So 13 is 1101, but you want to do 2's complement, so you need a leading 0. It's not a 6-bit representation. So that is equal to 13 base 10. Everybody kind of see that? So now we want the 2's complement binary representation of decimal number minus 13. So now I've got to do 1's complement, add 1, and that gives me an answer. Everybody sort of see that one? Is that clear? Any other questions about, this was question number 69. That was all right? 69. Any other questions about the midterm? No questions. No questions. Really? No questions? I'm scrolling through this now just to see if there's anything tricky that we need to do. All right. All right then. Well, hearing no questions, I guess we can go on to Chapter 6. Is that, unless we have questions about the midterm. And what that means to me is I get to do flip-flops, because you don't have any questions about the midterm. Right? Great. Okay. You guys, easy midterm. Easy questions. So, I'm sort of I'm impressed that you guys don't have any questions. So let's try something completely different. In Chapter 6, we see a flip-flop called a delay flip-flop. And there it is, delay flip-flop. And this is a synchronous Chronos is like the Greek god of time. So synchronous means in time. And the D flip-flop says that if you present a 1 on the input, during the next clock cycle that feeds into this little area in here, the output is going to be a 1. And if you put in a 0 on input during the next clock cycle, fed in through here, the output is going to be a 0. And what we do is we write out the present state, and then we write out the next state. Based on the input. So we can have 0, 0, 0, 1, 1, 0, 1, 1. So if the present state is 0 and you have a 0 on input, the next state is going to be a 0. If the present state is a 1 and you have a 0 on input, the next state is still a 0. If the present state is a 0 and you got a 1 on input, the next state is a 1. And if the present state is a 1, the next state is going to be a 1. And the way you represent the present state is we write Q, and the way in which we write the next state is we write Q plus. Q plus. So that's very interesting, all right, because now we can store. This is 1 bit of storage, also known as 1 bit of random access memory. We can just store by latching the 1 or the 0, and we can do that on a rising clock pulse or a falling clock pulse, depending on how we design our little delay flip-flop. Using more than 1 delay flip-flop, we can store multiple bits. So here's another delay flip-flop. And this will be Q0, Q0 prime. This will be Q1 and Q1 prime. And they both have a clock input. And what we want to do is we want to try and design a finite state machine. A finite state machine is defined as a machine which has a countable number of states. What we want to do is we want to go from a present state to a next state with a finite state machine. And we can draw a diagram for it. 0, 1, 2, 3. This is a little finite state machine. And it goes back to the beginning, right? And that's a finite state machine diagram. And this is called a counter. And today, we'll learn how to count. Like, just imagine the conversation you'll have at home over the dinner table. And what did you learn today? Oh, we learned to count to 3. What? What are we paying him for? So, yes, if the present state is 0, the next state must be 1. If the present state is 1, next state must be 2. If the present state is 2, the next state must be 3. If the present state is 3, the next state is 0. And that is a present state, next state diagram encoded into a present state, next state table. So far, so good, right? Now, it counts, goes back to 0. Here it's counting, goes back to 0. Simple, easy. Now the question is, how do we encode the present state and the next state? Well, we need 2 bits in order to count to 3. So what we do is we write Q0 and Q1. And we can do this by counting. And now we can write out Q1 plus Q0 plus, and this will be our next state, right? So we know we want to go from 0 to 1, so this next state is going to be 1. We want to go from 1 to 2, so the next state is going to be 2. We want to go from 2 to 3, so here's 2, we write out 3. And when we're in 3, we want to go back to the beginning, so we write out 0. How am I doing so far? All right, all I did was I made a binary encoding of the decimal present state, next state table. And something I know about the excitation table for the D flip-flop is, if you want the next state to be a 0, the input has to be a 0. And if you want the next state to be a 1, the input has to be a 1. And we're going to have inputs for D0 and D1. So here's D0, and here's, well, let's put it in order, D1 and D0. So if you want, you can just copy the next state directly over. And now we can see D1 is a function of Q1, Q0. And in fact, that function, D1, is equal to Q1 exclusive OR Q0, right? Because that's the exclusive OR operation. And D0 looks like it's got a small blemish in it. It's supposed to be a copy of the next state. D0 is equal to Q0 prime. Right? So D0, here's Q0. We've got to do D0 in terms of Q0. So what we'll do is we'll say if D0 equals Q0 prime, take Q0 prime and run it into D0. And then it says here, if D1 has got to be equal to exclusive OR between Q1 and Q0, then get your exclusive OR gate out. Put in Q1 and Q0. And here's Q1. And here's Q0. And now you've designed your first counter. How's that grab you? Cool, right? So this is a what they call a remapped excitation table. And what it's doing is it's giving you the present state and the next state in binary, and showing you what the excitation table should be for the flip-flops being used for your implementation. And yes, there's more than just D flip-flops out there. All kinds of interesting and wonderful flip-flops, which we can discuss as the course proceeds. Any questions about this? Your first finite state machine diagram. How exciting. I wasn't expecting to do this. I was expecting to do midterm stuff. But you guys are just whizzes and you didn't need it. Because, I don't know, because you're whizzes. Right? So this is an interesting question, right? I mean, you sure you guys don't need more review of the midterm? Because I can go on and on about finite state machines. All right. Well, let's summarize the D flip-flop as we understand it right now. This D flip-flop has a characteristic equation that says the next state, Q plus, is equal to whatever is on input for D. That's how the D flip-flop works. So if you want the next state to be 1, just make D 1. You want the next state to be 0, make D 0. And that's it. Let's try and design another counter. I think that's fun. We'll start this way. We'll start with a count. 3, 2, 1, 0, and we'll go back to the beginning. And what we'll do is we'll use instead of using subscripts, right, we're going to use D sub A with A and A prime, because I could call it Q sub A, but why bother? And here we'll have D sub B with B and B prime. And these both have implicit synchronous clock inputs, which I'm not going to draw. And now the question is, how do you hook it up in order to build a counter that counts down from 3? So we start with the present state, next state diagram, A and B, A plus, B plus. And if we're in 0, our next state should be 3. If we're in 1, the next state should be 0. If we're in 2, next state should be 1. And if we're in 3, next state should be 2. So you can see the present state next state diagram has materially changed because of the finite state machine structure, which has also materially changed. And now, using the characteristic equation that says Q plus must be equal to D, I can get D sub A and D sub B. And I know if I want the input to be 1, then the next state is going to be a 1. The input's 0, next state will be 0. This seems, I don't know, unnecessary, but I guarantee you that once you get to more complicated flip-flops, you'll see the necessity. And now here comes 1, 0. So now we can write by inspection D sub A is equal to A exclusive OR B inverted. And D sub B is equal to, well, B prime inverted. Just by inspection, because we're doing a 2-bit truth table and we're seeing the functions. So if D sub B equals B prime inverted, that's it. And if D sub A is equal to A exclusive NOR B, that's it. And now we have designed a counter, a finite state machine, actually a degenerate finite state machine, which is known as a counter. It visits each state once and only once, and doesn't necessarily have to go in order. It's still a counter, counting down. And any questions about this? D-flip? Yes, sir. You see there's this D sub A, and there's the function table. And I happen to know that if you have 0, 0, 0, 1, 1, 0, 1, 1, that A and B, A exclusive OR B is 0, 1, 1, 0. And then I go into A exclusive NOR B, and it's going to be 1, 0, 0, 1. So here you see 1, 0, 0, 1 matches that. So I said, oh, that's exclusive NOR. And I did it by inspection. I did it in my head. I just knew by looking that that was an exclusive NOR gate. I don't know if that's a good answer, but that's what I got. That's all I got. No, you could, if you don't know that this is exclusive NOR, what you could do is you could say that it's equal to AB, A times B inverted, and AB. So then you could write that D sub A is equal to A prime B prime or AB, which is the same thing as exclusive NOR. So if you did it that way, then you would be writing out that D sub A is equal to you'd get that. This is a rather less elegant way to write the same thing. But you could write it out that way, and that's totally correct. But writing it out this way is better because it's easier. Boy, that was fun. Wasn't that fun? So maybe we should try and use a different flip-flop. I think that's a good idea. I'll introduce you to my good friend, the toggle flip-flop. T for the toggle flip-flop says that Q plus is equal to T Q prime or K prime Q. Toggle flip-flop says that it should be T prime Q, actually. T prime Q. Q plus if you want to toggle, then what you do is you put in a 1. So if it changes, you put in a 1. Here it's changing, you put in a 1. Here it doesn't change, you put in a 0. You can do it another way. You can write T, Q. And then you can see what the output will be. Since it's 0, it doesn't toggle, so it maintains its state. Here it changes state, and here it changes state again. So toggle flip-flops look just like D flip-flops with a difference. And the difference is they have a T on input instead of a D. And if you put in a 1 during the next clock cycle, the flip-flop will change state. It'll change from 0 to 1 or 1 to 0. So, in fact, if you just put a 1 in there and leave it there, you made a buzzer. And this will just keep changing state and go bzzz as fast as it can. And so now, let's repeat the experiment where we create a finite state machine given the following finite state machine diagram: 0, 1, 2, 3, back to the beginning. Find a design using toggle flip-flops to implement the following finite state machine. So just like before, you do a present state, next state diagram. If you're going to number these things, you might as well number them in decimal. So if you're in 0, next state is going to be 1. If you're in 1, next state's going to be 2. If you're in 2, next state's going to be 3. And if you're in 3, you go back to 0. And now you have to figure out t sub a and t sub b, knowing that if you want to change state, you put in a 1. If you don't want to change state, you put in a 0. So going from A to A, there's no change in state, so there's a 0. But B is changing, so you put in a 1. Here, A is changing, so you put in a 1. Here, B is changing, they both get 1. This one, A is not changing, so you give it a 0. Here, B is changing, you put in a 1. Here, they both change, they both get 1. What is the value for T sub B? By inspection, T sub B equals 1, because it's changing on every state. What is the value of T sub A? By inspection, T sub A equals B. So now, how do we implement this? Well, let's see. We get ourselves 2 flip-flops, T sub A prime. Isn't this fun? B prime. We're designing counters. And we know T sub B is equal to 1, so put on 1. We know T sub A is equal to B. Take B. Bingo. We're done. That's it. My first toggle flip-flop based counter. Notice the simplicity of the implementation. All I needed was 1 and a wire. In other words, it was really an easy counter to build once you knew how. But knowing how was not so easy, at least not initially. Not initially. So now I got a question for you. We got a little time. Would you guys like to try your hand at designing a toggle flip-flop counter given the following finite state machine diagram? I'm going to splurge and get a fresh sheet of paper because I'm just a nice guy. So here's the finite state machine diagram, and we are going to design a counter that does this: 3, 2, 1, 0, blast off. And so the question is, given the following finite state machine diagram, design a toggle flip-flop based counter. And that is a perfectly legitimate question to appear on a final. Would you guys like to take a stab at it? Alvin, how do I start this problem? Yes, Alvin. Well, we gotta do something about a present state, next state table, right? So how about this? How about I start you off? We'll start with the present state, A, B, and I'll just number. Okay. And then what we'll do is we'll get the next state, A plus, B plus. And I will number the rows. And now you tell me, what should I write for A plus and B plus? So if I'm in state 0, what's my next state? So 0 goes to 3, right? So I got to write a 3 in here. So if I'm in state 1, what's my next state? There you go. And if I'm in state 2, what's my next state? Yeah, that's it. And if I'm in state 3, what's my next state? That's it. Does everybody sort of see what's going on here? You know, this is a very simple finite state machine diagram, but I need to start with a simple first example before we get into the complicated stuff. So now, next step is to determine what the toggle flip-flop inputs will be for T sub A and T sub B. And we know that if the state changes, T sub A has to be a 1. So Alvin, what's going on with A to A plus on row 1? Is it changing? And so what should T sub A be? A 1, there you go. And how about T sub B? Also a 1, there you go. And how about the next row? Excellent. And the next row? Well, 1, 1. Yeah, they're both changing. And how about the next row? Excellent. So now, what is T sub B equal to, Alvin? That's it. And what's T sub A equal to? Well, you got to do it in terms of the present state. And if you inspect it, you see it looks just like B, only it's inverted. Right? So T sub A equals B prime. Do you see that? So B is going 0, 1, 0, 1. T sub A is going 1, 0, 1, 0. So they're exactly opposite. And so now my countdown counter can be implemented using T sub B equals 1, T sub A equals B prime. Bang, I'm done. And that's how I count down using toggle flip-flops. Is everybody kind of following along on this? Is it making any kind of sense? So what have we seen so far today? We saw toggle flip-flops, and we saw D flip-flops. Other flip-flops include JK flip-flops and SR flip-flops. But these flip-flops have 2 inputs instead of 1, so they're rather more complicated to design with, although they're no more complicated to implement, and sometimes the implementations are even simpler. So that's a job for another day, teaching about JK flip-flops and SR flip-flops. But that's okay. I mean, we can definitely do that. So that's a good job. That's a good job. We did a couple of things today. I thought that was pretty good. Let's see what happens if we, well, I don't know, make up a circuit. Make up a circuit. So we'll do something like this. This is good. I like this. I don't know what I'm doing, but I'm not going to let that stop me. I'm making up a circuit, and it's completely random. I don't know what it does, but then I'm going to just sort of ask you a question about the circuit. All right. Given the following circuit, what kind of finite state machine diagram do you suppose this will generate? This is called reverse engineering. Basically, we start with a schematic and we say, what does this do? And we scratch our heads and we look at it and we go, how do we approach this problem? So what we really need is a basic problem approach. So let's write out some equations. T sub A is equal to A prime. And we can see that because of this wire. T sub B is equal to A. And we can see that because of this wire. So that's all right, I guess. And if we want to, we can write out the present state. Oh, let's label everything. Present state, A and B. And we can write out what we know. Let's just write what we know. T sub A and T sub B. And somebody said T sub A equals A prime. So here's T sub A, here's A. A prime would be 1, 1, 0, 0. And somebody said T sub B must be equal to A. And here's A, so we write it out. 0, 0, 1, 1, because that's what we know. We just write what we know. And then we can write out the next state based on our knowledge of what toggle flip-flops do to the present state. When they're a 1, they change the bit. When they're a 0, they do not change the bit. So here, A changes, B does not change. And so I get 1, 0 for my next state, A plus, B plus. Here I get 1, well, let's see. I get 1 because that's changing, and then that doesn't change, so that's 1, 1. And here I see a 0 is coming in, so that 1 stays the same. Then I see a 1 comes in, the 0 flips. Here I see a 0, so the 1 stays the same. And here I see a 1, flipping that 1 to a 0. And now I can write out the encoded present state, next state diagram in binary or in decimal. I like decimal. If you're in state 0, the next state is going to be 2. If you're in state 1, the next state is going to be 3. If you're in state 2, the next state is also 3. And if you're in state 3, the next state is going to be 1. And that is the finite state machine diagram for the circuit that I just drew at random. So this circuit, I had no idea what it was going to do. I just connected a bunch of stuff because I said, what the heck? And then said, oh, let's analyze it. And then I got this wacky looking finite state machine diagram that goes 0, 2, 3, 1, 3, 1, 3, 1, 3, 1, 3, 1, 3. And that's what this does. And that is your first example of reverse engineering. So what's the procedure? Well, you take the connections and you write out the equations. You take the present state and you use those equations to generate your inputs. This remapped excitation table will tell you how to modify the present state to get the next state. And once you know the present state and next state, you can extract the finite state machine diagram. And that's how you reverse engineer a counter. What do you think of that? Pretty slick, right? So let's do another one. That was so much fun. Wasn't that fun? That's very fun. Very fun. So here comes T sub A. Outputs are A and A prime. Let's take the outputs, run them into a well, let's just run them into another toggle flip-flop. T sub b. And now let's take b and b prime. And now let's take b prime, and we're going to take that and we're going to run that into T sub a. Given the following, find the finite state machine. Isn't this fun? And the answer is yes, Professor Lyon. Very fun. Very fun. Very fun. Let's see, who can we call on that we haven't seen? I'm going to go to the bottom here. Get somebody new. Julian. I never call on you. Julian, what should I do here? Well, let's start by stating T sub a. What's T sub a equal to? Yeah, it's equal to b prime. That's it. And what's T sub b equal to? Well, it's equal to a, right? Because we have T sub b hooked to a. All right? So now let's do the present state with a and b. And let's write the remapped excitation inputs, T sub a and T sub b. So now, what should I write for T sub a? Yeah, we're going to go down the row. That's it. And now what should I write for T sub b? There you go. So now I can get a plus and b plus because I know what toggle flip-flops do. They cause things to flip. So if a is a 0 and you have a 1 on input, what's a plus going to be? Well, you're going to flip it, right? 0 gets flipped because you got a 1 on input, so that becomes a 1. Here, 0 doesn't get flipped because you got a 0 on input, and so it remains as 0. So toggle flip-flops only flip when there's a 1 on input, and then they'll flip either from 0 to 1 or 1 to 0. They change state. They toggle. So here there are zeros, so nothing changes. But here they're both 1s, so what will the next state be? So the 1, 1 means both bits will change. If the input starts at 1, 0, and they're both going to change, what will the next states be, do you think? Okay, so the 1 will change to a 0, and the 0 is going to change to a 1, right? Because they're both going to toggle. That's how these things work. Did you see where I'm going with this? You know, if you input a 1 on T sub a, the a will change to a 0. If you put a 1 in on T sub b, the b changes from a 0 to a 1. Let's try the next one. Do the next one for me. So now I got 1 and 0. That's exactly right. That's exactly right. So it looks to me like you should be able to identify the present state and the next state. Right? From 0 we go to 2. What happens if we're in state 1? What's the next state going to be? That'll be 1. So 1, once you're in state 1, you stay in state 1, according to this. And what if you're in state 2? What do? There it is. And if you're in state 3, what do? That's it. So this wacky counter that I just designed does the following. It goes 0, 2, 1, 1, 1, 1, 1, and if you end up in state 3, it goes 3, 2, 1, 1, 1, 1, 1. And that's what it does. And that's how you reverse engineer a counter. Who got confused by this? So we've got to do some reading now. This is kind of important stuff. It's the next step in the course. It's the second half of the course, and it goes to chapter 6. So what you'll want to do is start your reading on. Can you see any of this? There it is. You want to start with the sequential logic design. Chapter 6, page 282. So let me just jot something down for you. Chapter 6, page 282 is where you want to start your reading. And you're going to see all this interesting and wonderful stuff about D flip-flops and SR flip-flops and latches and let's see, right in through here, this is where you're going to find the present state, next state excitation equations. This is the characteristic equations. And so we were just doing this one, the D flip-flop, and this one, the T flip-flop. But these are the other flip-flops we haven't done yet, SR and JK. And we can do those again, or we'll do those another time. I don't think we have enough time because it's 12 minutes after the hour. So you'll want to be reading right up through the point where you get to page 311. So 282 to page 311, and that'll get you right up to the point where you have exposure to the different flip-flops. That'll get you caught up to where we are today. If you have any problems with the midterm, please bring them with you on Monday, and we can certainly try and address them. Otherwise, we'll continue this discussion about the second half of the course, which is on sequential circuits. And so enjoy the rest of the day and have a nice weekend, and thank you for your attentions. Thank you. Thank you.